of Professor Brende, error analysis of fixed point, iteration procedures, what he discussed in the earlier one also. Please settle down yourself, because we are having some very hectic time today. This is the last and we have to finalize everything on time. So I have some announcement also for you people. All the lectures given by Professor Brende, me, till yesterday, I have uploaded all those. I posted all those in our Gyan WhatsApp group, all, this morning, except few pictures. Mobile pictures are loaded into the Gyan that group, but the photographs which are available in the camera, it will be posted later on, because that needs little bit time to post on the group. Okay, so this is what the announcement is, and after this we have one more lecture, and you will have the lunch, and after the lunch there is one lecture by Professor Veeramani, and it will last till 2:45, and 15 minutes just gap, and we start our validity function. Okay, and in the validity will be fixed for 3 to 4 p.m. only, and as soon as it is 4, Professor Brinde and Mrs. Brinde, they will proceed to Raipur. Okay, so this is what the announcement is. So in the validity function, the participants will receive their certificates also, if time permits. Otherwise, at least the outside participant they will receive, and the local participant, they take the certificate after the validity function. Okay, thank you, and I request Professor Brende to continue his lecture.
Thank you. So continuing this announcement, I have a very special request to you. Especially, I'll prefer pictures with ladies. I want to impress my colleagues, because I have a meeting on Monday. So on Monday, next Monday, I have from 8 to 12 lectures, so I have classes. I want to impress my students to show some pictures at the beginning. So please send me by WhatsApp all kind of picture, but I want to make jealous my colleagues. So in the department, I have meeting of the department, I'll show them some pictures, and they will be very jealous about the fact I have picture with so nice ladies. So they will be interested to visit India then. This will be a good advertisement. So please send me any picture with any kind of group involving myself, okay? Then let's go further. So when dealing with iterative schemes in general, with fixed point iterative schemes, we have these difficulties, these drawbacks. So we cannot get analytical estimate of the type 1. We cannot get an analytical estimate of type 2, or we get an estimate of type 2, but it is not relevant, like in this case. So we cannot decide by the concept number 2 that a sequence, an iterative scheme, converges faster than on the other one or not. So we need another kind of order of convergence. This is why I consider this third type of rate of convergence. And I introduce this one. So we have two sequences. AN converges to A, BN converges to B. These are real real numbers. We discuss first for real numbers. And if these sequences have this property in the sense that this limit exists, then we have these possibilities. First, if this limit is 0, then we should say that the sequence AN converges faster to A than the sequence BN to B. If L, this limit, is finite and is greater than 0, is not 0, then we'll say that these two sequences have exactly the same rate of convergence. And there is the other case, of course, if L is infinity, is the reverse of case A. This means Bn converges faster than En. But this is implicit. So we denote this fact in the case A in this way, with small o. So An minus A is a small o of Bn. So keep in mind what does it mean O of big O of something. And what does it mean small o of such sequence. These are different concepts. And I did this for the first time in this paper, which was published in 2004 in this journal, which changed its name. Now it's under a different name. It's something else. Fixed point theory, and in engineering and application, it is again of a journal. It was stopped. The editor was Agarwal, R.P. Agarwal. Hindawi. Then it moves to Springer. Then this journal was stopped to being indexed in Web of Science maybe for 10 years or more, and now it is again. Again, they succeeded. I was an editor at this journal, but I resigned for some personal reasons some 3-4 years ago. And this paper is extremely highly cited because a lot of people found this idea useful when, once again, I repeat this situation. So we cannot have any information of this type, or this situation occurs, we cannot say nothing. So in that case, we can sometimes use this concept. We can apply this concept to several cases. So I'll show you one such situation. For example, we have the rate of convergence of type 2 equal 1, which we have seen is not useful for us to decide about the convergence of these sequences. So I consider the following situation. We have two iterative schemes which generates the sequence xn and yn, and they both converge to a fixed point P of a certain operator T, and we have these error estimates with big O. What does it mean? This means xn minus P is less than C1 alpha n, an, this is an, and xyn minus P is less than a constant C2 and times Bn. This is what we know. These sequences, we have seen both sequences tend to 0, because such kind of error estimate is not useful if this right-hand side is not a sequence tending to 0. It's not useful at all. So in that case, if we can prove that this numerical sequence, this is a number, a sequence of numbers, real positive numbers, converges faster than did this sequence of numbers appearing here, then we can say that our sequence xn converges faster than yn. This is a concept I introduced in this paper I mentioned before, and it has been taken into consideration by many mathematicians. Of course, it has some drawbacks also, because these estimates, in order to get good information, and we can infer that we have this conclusion, xn converges faster than yn, then this would be the best error estimate, best estimate. I mean, it is possible to have, let's say, C1 an prime less than C1 an. So in that case, this sequence will be useful. So we should suppose these are the best estimates. So in that case, the information is okay. There were some mathematicians, mainly Romanian, who objected about this concept just a few years ago. They are friends of mine, friends in, you know, what does it mean? So they wrote some negative papers saying that this concept is not correct. It's correct if we have the best estimate here. I wrote a paper as a response to their objection. Their objection were in some sense correct, in fact. So this is about rate of convergence. But as I said, almost all fixed point iterative schemes have linear convergence. So it is possible in some situation to improve this slow convergence, this linear convergence. I show you just a few facts about the research done by one of my PhD students. Juana, it's a female name, so she's a girl, well, she's now married. Juana did this work on accelerating fixed point iterative schemes. So we have a fixed point iterative scheme. It converges slowly in this sense, or in the other two ways I mentioned, concept of rate of convergence number 1, number 2, and so on. And she published a few papers about her research. These are some of her papers about accelerating. And I want to show you just how she did. This is a very natural way, and it is related, strongly related to the average technique, the convex combination technique. Always this method leads to better results. And look, we have this, it is denoted by T of x with parentheses. So we have this fixed point problem. The Picard iteration is this one, and we introduce together this type of acceleration method. Well, we converted this problem of fixed point problem into another fixed point problem. And look, if we define this T lambda in this way, what is this? Here, it's lambda 1, I did not mention, they are determined in such a way, it is a linear combination actually. It's not a convex, but sometimes it is convex combination. And it is similar to T lambda I considered in the other context when I spoke about enriched mappings. And what is this T lambda of X? We are in that case on the real line to avoid any difficulties. So in that case, we construct this T lambda in this way, and you can see that when we multiply here, this equal X, we'll have X equal T lambda X will be exactly X equal Tx, because all these will disappear when we cancel the identic terms. So we are interested, for example, to find this lambda 1, lambda 2, lambda k. They can be determined in such a way to ensure a rate of convergence in the sense of concept number 2 better than 1, because usually for Picard iteration, I have told you, this kind of iteration has rate of convergence 1. So for these new iterative schemes, PADE type, PADE is the name of a mathematician, will have R greater than 1, sometimes even 2. So this is a method to accelerate a fixed point scheme. There are some other ways, and you can see here this one is PADE type accelerating method of Picard iteration. This here, it's another algorithm, a B method to accelerate iterative schemes. And another concept, Aitken method to accelerate iterative sequences, and some others, I forgot about this. Epsilon algorithm, this is so at least 3 or 4 methods we have. This is generally necessary to do this when we have slow convergence. If you remember, I presented a result to this split feasibility problem. Not yesterday, the day before yesterday, and there were some numerical experiments for the authors I quoted. They obtain a good approximation after 10,000 iterations. So this is very slow convergence. I don't remember exactly what was the number, but it was something like 50 something or 60 iterations. So we succeeded to get such a good convergence for our algorithm. This means we in fact accelerated, but in a different way, this. So now let's come again to this situation about studying the rate of convergence. We are in the situation we cannot estimate any of these ones, number 1, number 2, number 3. So what can we do in this situation? So we can test the rate of convergence empirically, we say. Empirically means by experiments. This is a Greek word, old Greek word for experiments. And some of these such kind of results are included. Even in my book, I included some numerical results obtained by this fixed point software. I didn't know this is a Hewlett-Packard machine. On my computer, my software, this one, fixed point, It was designed by one of my PhD students. This software package allows to study empirically the behavior of a certain iterative scheme. To understand what happened, I'll graph here the simplest situation. So, we have this Picard iteration. I wrote in this way because we are usually using this notation for functions, and here we are working for function. What does it mean that xn is t of xn? This means that the point of coordinates xn plus 1, what happens? It belongs to the graph of t. This is the significance of this iterative. So, if we have here the system of coordinates, Cartesian system of coordinates, x and y, let's say, and we have a function I denote in this way to suggest we are in the same situation. Let's say this is the graph of function, this is y equal t of x. What happens? What does it mean xn? We are here, this is xn, and the fact that xn plus 1 is t of xn, this means this is the point of coordinates xn plus 1. Right? So, we can represent the orbit of this dynamical system, because this is a dynamical system. We start from an initial point and we can draw the trajectory. And the trajectory will be in the following way. I'll show you more examples just to start from an initial value. So, just to tell you that this is a paper describing the implementation and application of this fixed point software, written together with my former PhD student, Bozantan Andrei. He's a very bright, he was a very bright person, very strong programmer, extraordinary programmer. He used to be in my department as an assistant professor. I was very happy with him because he was very good, and students enjoyed very much his lectures, and especially tutorials, laboratories in programming. He's an expert. But, you know, he left for software industry. He was attracted, I don't know, Google or Microsoft or some such company hired him for maybe 10 times bigger salary than in at the university, and he left. He told me, "Professor, please don't be upset on me. This is very important for me." And he moved. Even he moved from Romania somewhere, I don't know in which country, to work for, I guess, for Microsoft. Anyway, it doesn't matter. So he did this nice package, and his thesis is this one. He used this PL homotopy algorithm is used to solve problems when we apply Brouwer fixed point theorem. So it's about computing fixed points related to unconstrained optimization problems. Very nice thesis, and he also did some other papers related to implementation of this algorithm. very difficult problem to implement such an algorithm that I worked 40 years ago. So let's see what is the trajectory of our iteration. So let's say we start by x0, right? Here we go, I'll indicate in this way, this is the first iteration, x0, x1. Okay, to get the next step, I draw the first bisector. And what does it mean? This is the first bisector has the equation y equal x. We are here, this is x0, this is x1, and we go here and we find on the x-axis, this is x1, right? But we now compute t of x1, this will be x1, x2, right? So we are here, we come here, we come here. Now the orbit, how we'll do this? This will be here, this is x2, and we go to the first bisector, and this is also x2. So this is x2, x2 on the x-axis, and what is x3? x3 is t of x2. So this is x3, and so on. Now we continue in this way, again to the first bisector. This will be what? This is x3 measure here. This, okay, my drawing is not accurate, so this will be just equal. Here we have a rectangle. It's not a rectangle. This is exactly x3, and we continue. This is x4, so x3, x4, and again we go to the first bisector. This will be x5, and so on. This is the trajectory of our iteration. Is clear? Because it will be important to understand our numerical experiment. So, such a graph will show how behaves our trajectory. Where is the fixed point of this map? The fixed point is here, at the intersection of y equal x and y equal tx, because this is the fixed point. So this is our fixed point. At least, as we can see here, this fixed point, we don't know what will happen, but the next will be coming here, then it will go there, and it is possible then we'll have no convergence. So this kind of experiments will show us if our algorithm xn plus 1 equal t of xn produces a convergent algorithm or not. In the second step, it also will tell us about the rate of convergence. And look, I'll skip the stability and I'll come back later because I want to show this, and I'll come back to, this is the screen of this fixed point package. It is designed for Picard iteration, Krasnoselsky, Mann, Ishikawa, Prešich 1, Prešich 2, when is this multi-step iterative schemes. Here we introduce the function we work with. You can see is our function I use. So x plus 1 to the power 1 over 5, what we